Okay, so I'm Elad. I've recently joined Mellanox, and today we're going to talk about multipath RDMA. So the main motivation for the multipath RDMA actually is having a support three types of features. We would like to have a good support of failovers, bandwidth aggregation, and to support layer 3 data centers. And what we see in this drawing is actually having two hosts talking with each other, and both of them has two networks that they can talk to. And what happens with if one of the networks are failing is that all the resources within this network are failing as well. And we would like to have a solution that those resources will simply migrate to the other path, to the other network. What you don't see in this drawing is what the network is. I mean, the network here is not well defined. And there is a good reason for that, because it's not need to be defined. We don't care in multipath RDMA what is the network. It can be a different layer 3 network. As you can see here, there is a completely different net mask in those networks, or it can be a different fabric. It can be InfiniBand, it can be Rocky, it can be even soft Rocky. We don't care. Another strong motivation that we would like to do is having a live migration. And a live migration meaning that we would like to keep the traffic going on while the VM are being migrating from one machine to another. In this example here, we are seeing even a worst case scenario where the machine that we are migration from as an InfiniBand SRIOV solution, but the machine that we are migrating to has none. So how can we do it? So what exactly is multipath RDMA? So it's a software solution only. It's hardware agnostic, it's backward compatible, and it created something that we are calling it layer 3 session, as we can see in this drawing. Now, the layer 3 session means that once an application initiates a connection, the first connection with the other peer, there is a primary flow. And using this flow, we actually discover all the different subflows between these nodes and the different hardware devices, addresses, or whatever, and we simply prepare them on the side. Well, layer 3 session isn't something new. I think that Tom here talked about it yesterday, Tom from Microsoft talked about it, about Microsoft SMB 3.0 implementation, that there is some kind of a session. If we have RDMA devices, we simply use it. If we not, we are fallback and using ordinary Ethernet packets. So also iSCSI has some kind of a session concept. So why won't we take it into the verbs and extended the verbs to contribute that other application can use the same feature, and also they can use it without any need of doing any kind of modification. So that's pretty cool. So let's talk about how the flows are being created. So what we are seeing in this ladder diagram is actually an application that initiates a connection via RDMA CM. It can be also in other ways. And basically talk with our MP-RDMA device. And our MP-RDMA devices stated that the initial flow will be created using physical dev 1. Again, it's abstract RDMA device. It can be even soft Rocky. And once this flow is being created, we are negotiating via private MADs, and we are doing something which is very similar to MP-TCP. That's the name it's coming from. That we are exchanging capabilities about the different addressing between the two nodes. And then in the background, we are preparing subflows, which are in standby mode. We don't use them unless there is some kind of migration failovers And in those events, we are simply changing the path from the primary flow into the subflow. So this is what MP-RDMA are about. Let's see how we are doing this migration, because this is one of the main questions. So these slides probably look familiar because it's taken from last year's presentation about RDMA bonding that was given by Liran last year. And basically what we are doing is we are monitoring the work use of the application and having some kind of a concept about virtual producer and consumer. And every time that we want to change a flow, we know exactly how many work elements are in a standout, and we can simply re-enqueue them. So there are a couple of more solutions that support failover or bandwidth aggregation, like APM and Rocky Lag. One of the main differences between them and the multipath RDMA is the layer-free session that I talked about. The multipath RDMA has a concept of a session which allow him not only to fail over ports or doing aggregation within a single card, but also extend that to have a multi-device support and migration support. Okay, so as I said before, MP-RDMA is being molded by the multipath TCP specification. So there are a lot of similar ways between the MP-TCP and the MP-RDMA. One of them is that all the capability exchange and the addressing exchange of the subflows is being inside the primary flow. With MP-TCP, it's being done using TCP options within the TCP header. We are using private MADs in order to understand all the peers addressing and create some kind of convolution for all the subflows. But there is a big difference that MP-TCP uses the socket as the endpoint and the byte stream as the data sequences. And again, we are RDMA. Our main goal is performance. So we are bounded to use MP-RDMA device. And the QP is the way of doing the data itself. And we will see it in a couple of more slides about the data path, but actually we are using the physical QPs directly to the application, and we are posting the actual work use inside the QP. And again, this is for performance. We don't want to virtualize that. Okay, so let's talk about the design. We have two components that we have created. We have a user mode verbs extension and a IB core device inside the kernel. Both of these features pretty much act the same. They are both responsible about the physical underlying resource creations and handling failovers. There is another feature where we are working with, which is the RDMA CMA, and we are using actually this feature and the address translation within this module in order to create all the different subflows. Another cool concept that we have integrated inside the MP-RDMA are policies. And I presented here 3 policies. One of them is active backup, which means that if I have 2 devices and the first device has free QP resources, I would like to create a shadow QPs for the subflows in the other devices. Another policy that we would like to take care when we are creating the underlying resources is with load balancing. If I have 2 cards, I would like to shape the traffic to gain some load balancing. And the third bullet is efficiency, where I'm actually understanding the application and the application constraint, and if an application using shared receive queue or completion queue, I will want to create the QPs in the same device in order to have like one-to-one call with the application. Of course, I can do a mix match with other devices over different fabric, but then I will lose performance. So this slide actually showing how the namespaces within the MP-RDMA concept is working. And again, it's very similar to MP-TCP. So once an application is open a connection, it gets virtual resources, virtual QPs, virtual MR, virtual PDs, virtual CQ, and it's up to the policy to decide on which underlying device I'm going to create my resources and then map the data path or management operation to. So we can see here, for example, from the efficiency policy in the previous slide, that QP 82 and 61 are being created under the same shrek. Another idea that we have introduced in here is actually lazy creation, because the namespace is too big and the multiplication of all the subflows is very resource consumption. So we have decided to use some kind of lazy resource creation, which means when an application uses a virtual QP, the policy decided, okay, let's bound it you into device, RDMA device 0, port 1. Again, I don't care what is the underlying device. It can be Rocky and it can be InfiniBand. So when the policers decided, okay, I'm going to bind the virtual resources into the underlying QP, I want to create a physical QP. And when I'm doing that, I understand, okay, I need to create a underlying PD for this QP because it doesn't exist in the underlying device. So I created. And then I say, okay, the QP uses a virtual CQ. Oh, okay, but I have it in the underlying device, so I'm going to use it. And only when I'm doing post-send and I actually need the memory region translation, only then I'm creating the MR. Okay, so these slides talk about the data path. And the data, again, the most critical thing with MP-RDMA is actually it's a software solution that adds overhead to the data path, which is not so good if we want to do a performance. On the other hand, we gain a lot of features that we couldn't do otherwise without this abstraction layer. So what I'm showing here is actually what are the translations that I'm doing in the data path, and this is very critical, and it's supposed to be as less lock-in as possible. And what I'm doing is actually translating the virtual QP numbers and the physical underlying QP numbers. I'm also translating the local MRs or R keys of the MR if I have them in cache or not. And of course, I'm monitoring the virtual work queues as I've described again in the subflow migration. I need to monitor the work queues itself because if I want to migrate to a different path, I need to know exactly how much outstanding work queues I have in order to re-enqueue them. Now, this data path model is seamless to the application, and this is very important to say that everything that I've presented so far is agnostic to the application. Application continue to use the lib-IB verbs. It just uses MP device as its underlying device, and I understand everything that's going in the underlying and all the possible flows in order to connect those two devices, including, again, the data path. The application just doing post-send and post-CQ, and that's it. So we have some initial results, which are very encouraging. And it's not a fine-tuning to performance. What we wanted to measure here is actually how much overhead we are doing in the data path. And we are seeing here a very close by graph according to the message size, which is on the bottom, about the latency and the bandwidth. And we are seeing around 2% overhead in large message, go down to 5-7% in the average message size, and go down to around 10% in, 10-12% in small message sizes. Okay, we have a lot of work ahead of us. We would like to finalize the MP-RDMA driver, and most importantly, we would like to finalize the connection model, which is the most complex entity in this MP-RDMA concept. We also want to have some kind of a standard about device removal, and this is something that we need in order to support live migration, because suddenly someone take our underlying device, and I don't have any way to communicate with the other peers, so I would like to know that something is going on. Also, we need to finalize RDMA and atomic support, same as for datagram and multicast support. We would really want to have some kind of a standard for this feature, whether it is in the IBTA to extend the CMA for the MP-RDMA verbs, have some kind of RFC, and of course, have this code in open source. I think that many other vendors can enjoy this type of capabilities and interoperabilities. Okay, so to summarize everything that is being said in here, and I see that we are a little bit ahead of time. So MP-RDMA come to solve a couple of customers' requirements to have a failover in multi-device, multi-home host, to have transparent migration and bandwidth aggregation. We know that we are in a good path because we took our concept from MP-TCP. So it's a very good point to be in. We are not the first one we are doing it, we are just doing it over RDMA. And we have some promising initial results that the namespace translation is not so much costly. Okay, so if you have any questions.
Okay. So you showed us the performance charts. Which benchmark did you use? Something else?
Yeah, I use the perf test, the IBSend LT, and the IBSend bandwidth. This is what I'm using. Again, the main concept here is not to have a complete performance results, because we are not yet there. We just wanted to measure initial results about the overhead that we are adding. And we have work to improve that, but it's something that we can start work with. Any other questions? Yeah, yes.
This will be available when?
So the question is when it's going to be available. I'm an engineer that writes the code. Again, there are some missing parts. We do hope as soon as possible to have it, at least some kind of skits into the open source. I don't want to commit to any schedules. We will see some customers already have interest in that, and if anyone wants to learn more about it, he's welcome to come and approach me and talk to me, even after this conference. Yes. No, just a second. He was first. Sorry.
This code base, that's all user level code currently? Or is that also?
No, it's both kernel code and user space code. Right now, it's implemented only over the libiv verbs, Linux implementation. We have a plan to migrate it into Microsoft Network Direct.
And comparing that to multi-part TCP, how would you do load balancing here? In multi-part TCP, you have the knowledge of the current usage of your lines. If you do that follow up in the stack that you are having multiple devices.
Yeah. Okay. So the question was how you're going to do the load balancing here. Meaning with MP-TCP, you know exactly how many bytes are going through each device, so it's very easy to do the load balancing, and here you're working over the verbs. So we are not so much accurate as MP-TCP, that's correct. This is because we have one-of-one translation between the virtual worlds and the underlying physical resources. However, we do have some kind of a polyser, and the polyser is something which is abstract, and every user can write its own type of policies. And one of the policies that we have written is actually counting on each physical devices how many post send receive are being occurred and what is the bandwidth over there. And when there is a new QP, we need to say, okay, device 0 is very busy. It's most busy. Okay, we will not create this resource there. We created on the least used devices. So this is how the load balancing occurs. It's not exactly 50%, 50%. We are splitting the traffic according to QPs.
I mean, the main question is now to equally distribute what we learn, which link is more.
Yeah, okay. Yeah, so.
So
So again, this is what we are doing. Since we are monitoring all the virtual work queues, we know which device is more busy. We can see that. It's simply a counters that we add. Just a second. Did you add a question?
Well, so I did have a question about load balancing, but the
Okay.
mechanism for releasing does a big stack of software, right? There's some kernel and user space. So what would be the mechanism for the release of that, right? So how would we line ourselves up to be able to test that or to...
Yeah. Okay, so the question was, you're going to present a big stack of code. You have both kernel mode driver, user mode device, and all the namespace translation, and that's correct. It's a big project. It's not something little. We are going to put everything in the GitHub so other vendor can just compile and run. We have a plan on integrated into the OFED, Mellanox OFED stack. Again, I don't know when. I think you asked this question. I don't know when, but this is one of our plans. I think that every vendor that has RDMA can simply compile the kernel module, do inst mode, and compile the verbs and add driver by himself. Because I'm discovering, one of the first things that I'm doing is discovering all the other verb devices in my world, in my machine. And I'm trying to communicate in order to understand all the subflows. So besides just compiling to the specific verbs, libraries, and the kernel module that you're working with, there is nothing else that you need to do. Everything is inside the code. Okay, so Tom had a question.
Yeah, I have at least two questions.
Ooh.
Memory regions. How do you get away with just registering on one NIC? I mean, shouldn't you be doubling your memory registration overhead and registering on both? Because the upper layer might issue its request at either one.
Okay, so this is the question that Tom is asking with the memory region. Well, memory region is not bound to a specific machine. Memory region, it's two devices from both sides registering MRs and communicate the R keys and have L keys inside.
But the memory is named by the handle, and that's the application's choice, how he uses it. It's assigned by the handle. It's assigned by the
Okay, so please.
If he launches an RDMA operation on the other NIC, because you routed it there, it's going to fail. How does that work?
Okay, so let me answer your question. Again, the question was with the MR and how exactly you are going to map the application memory. Well, if you look in this slide, and this is explained very good, I'm extension of the application, which means that when application is registered, the MR, I know its virtual address, and I'm living in the same context as the application. So I have access to the virtual memory. And then the mapping is doing simply, I just remember the virtual address pointer and the length. And when I'm doing the underlying resources, I'm within the same thread with the same context, and I simply initiate the same MRs. Okay. So this is one.
This answers my other question, and that is how do you preserve ordering?
So wait a second about the ordering questions. I would like to talk more about the MR and the L keys and the R keys. Okay. So specific, if we are doing a send operation, then it's very simple. Just using the MR for the local memory. I don't send in the keys to the remote peer. So it's easy, it's one-on-one solution. But when you're using RDMA, and this is something that...
It's not an L.
Yeah, okay, so exactly. So when we are using the R key, we're actually doing our own negotiation, because when application register an MR, we are sending her the key. And we are having some kind of associative array.
You might send a dozen MRs.
Yeah, so for each MR, I need to do another inbound round trip with the other peer in order to understand.
You're going to keep
Okay.
inside as RDMA writes and fragment as SGE to go to each NIC that you happen to register the memory on?
No, I don't. No.
I just don't
No.
understand how it works.
Okay, so I will go to this ladder diagram, and I'm going to use it in order to try to explain. Again, we are a little bit out of time, so if I will not able to give you a full answer, please come and catch me on the break. I will be happy to talk about it, because this is what I did. So when application is actually doing a post send and giving some kind of R key to our application, we are looking here in some kind of associative array and understand, okay, we don't have a translation to this R key. I don't know this resource, because this R key is being created at the other peer. So I'm using the main flow and the mods and sending him some kind of a free way. Okay, I have this MR, can you please resolve it? And then he send me, okay, this is the, and then the other peer simply create underlying resources of the MR, create a physical, because I know the connection and the flow is from one device to another device. So I create physical resources MR in the other side, and then I send, okay, this is the underlying R keys that my hardware has.
Your two MP-RDMA implementations are defining a new protocol between each other?
Yeah, this is the connection management protocol. Yeah, this is something that is must. And for backward compatibility, and this is something that maybe I didn't emphasize as much, is when I'm starting to do the initial connection, I'm sending private mat with the MP capable exchange. Now, if the other side is not MP device, it simply don't answer me. And then I'm doing a fallback. I'm continue to be one-on-one on the verbs. But if he answers me, I know that he has some kind of MP device on the other side that listens to these MADs, and I can use this sidebind protocol in order to exchange information. Yeah.
It seems to me you need a very simple and well-defined upper layer, perhaps a non-transparent solution by which the upper layer tells you where to route to make this all work. We can talk about it. But.
Okay, so let's talk about it. I saw there another question before the break. Do I have more time? Or? One more question. Okay, yes.
Okay, if I understand you correctly, you can have an application posting an RDMA write, which will be sent to, let's say, the first device. Subsequent, the application posts another RDMA write, which is actually executed on another device?
No. Okay, so the question is, okay, if you are doing post-send, it's going route into device A, and you do another post-send, and it's going into device B. No, we are, and this is the slide here. The QPs is being bounded into a physical device, and it's one physical device, and that's it. And this is where the QP is living at. All the post-send, and this is again for performance, all the post-sends and the policy queues are being generated within this underlying device. And only if it's failed, or there is a migration, or the load balancer somewhere decided to shift the traffic, only then we are going and doing this failover mechanism. And this failover mechanism is actually created another underlying resource in another device and shipping the traffic to it. But once QP is being bounded to a specific physical device, it's being stay there. And again, this is purely for performance, and maybe it's related to Tom's question.
You cannot really take advantage of both interfaces in order to achieve higher bandwidth.
Yes, and this is one of the questions here is how you're doing the load balancing. So I'm distributing the QPs between different devices. But the concept is that, and this is here, the concept is that we are not living within the byte stream, we are living within the QP worlds.
So a single application can't take advantage of the multipaths available?
If a single application, single QP, no. Okay, thank you very much. If you have any more questions, please come look for me.